Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine, just for a second, that you are looking out your window at this towering thunderstorm.
Right.
The sky is that bruised purple color. The lightning is just strobing. And deep down, it's about to drop a completely catastrophic flash flood right on your city.
It's a terrifying scenario, yeah.
It is. But hey, so what if I told you that to predict exactly when that specific storm will turn deadly, you actually shouldn't be looking at the rain falling out of the bottom.
Exactly.
And you shouldn't be looking at those massive, anvil-shaped clouds at the very top either.
No, you really shouldn't.
Right, because to truly understand the destructive power of that storm, you actually need to look directly into this invisible vertical elevator shaft in the exact middle of it.
Which is, frankly, the ultimate blind spot in modern meteorology right now. I mean, we see the aftermath and we see the exhaust, but the engine itself has been essentially hidden from view for decades.
And that is exactly what we are unpacking today, because we are looking at this profound, honestly, almost unsettling contradiction in how our entire planet operates.
It really is a paradox.
Right, because on one hand, you have the absolute most fundamental thing you need to survive, which is water.
Yeah.
More than half of the entire world's life-supporting fresh water. I mean, the water that fills the reservoirs you drink from, the water that grows the food on your table, the system that essentially keeps human civilization humming, it all comes from tropical convective storms.
It's basically the delivery mechanism for life on Earth.
Exactly.
I mean, without that massive global transport of moisture, the planet as we know it simply doesn't function. We would be in serious trouble.
But then you have the dark side of that exact same coin.
Yeah, the destruction.
Right, because these storms, these literal engines of life, are also responsible for some of the most extreme, terrifying, and just life-threatening weather events on Earth. They cause devastating floods, they generate hail that destroys entire crops in minutes, they spawn tornadoes, they wipe out power grids.
This is a massive, massive paradox.
It is. How can something so incredibly vital to your everyday survival also be so inherently destructive?
And honestly, that duality is exactly why atmospheric scientists have been so relentlessly obsessed with them for so long.
Right.
We are completely reliant on this massive system that we just don't fully understand. And, well, more importantly, it's a system we can't perfectly predict.
Which is the scary part for most people, right?
Exactly. I mean, we know they bring the water, and we know they bring the danger. But the precise, actual physical mechanics of how a storm decides in real time to be just a gentle afternoon rainmaker versus a catastrophic multi-billion-dollar event, that exact tipping point has just been completely obscured from us.
Which is why I'm so fascinated by this upcoming mission from NASA. It's slated for 2027, and it's called INCUS.
Yes. Investigation of Convective Updrafts.
All right, INCUS. And from what I understand, it is this incredibly complex, highly synchronized orbital ballet designed to finally crack open that mysterious vertical engine of these tropical convective storms.
It is. It really is.
But I'll be honest, the deeper I look into this, the more questions I have about how they are actually pulling this off, logistically.
I don't blame you. It is arguably one of the most ambitious and, well, elegantly designed pieces of atmospheric science ever attempted.
Wow.
Yeah, it represents a fundamental ground-up shift in how we actually look at the Earth's atmosphere.
And for you listening right now, I want to make it super clear that this isn't just some, abstract astrophysics or a high-level meteorology lesson.
No, not at all.
This is about the immediate future of how humanity is going to physically protect its cities. This is about how your local government is going to manage your drinking water, how your homeowner's insurance is going to be calculated even.
Yeah, that's a huge factor.
And exactly how much warning you get on your phone before a flash flood literally cuts off your street. It is that direct to your everyday life.
It really impacts everyone.
So, okay, the core objective of this INCUS mission is to measure something called convective mass flux.
Right, convective mass flux.
And I understand those words individually, sure.
Yeah.
But what does that actually mean in the context of a giant thunderstorm?
Well, to really understand convective mass flux, we have to kind of fundamentally change our perspective on what a storm actually is.
Okay, I'm listening.
Think about how you usually interact with the weather. Like when you stand outside during a thunderstorm, or when you just pull up a weather app on your phone, you are experiencing the weather horizontally.
Oh, right, like on a map.
Exactly. You look at the radar map and you see this green or red blob just kind of creeping from west to east across the screen.
Yeah, exactly.
Or you step outside and the rain is falling down on your head. We treat storms like they're these flat, horizontal phenomena, but a storm isn't a flat circle on a map. It is a towering, three-dimensional, incredibly violent vertical engine.
Okay, so the convection part, that's the vertical movement. It's basically the hot air rising, right?
It is, but it is so much more violent and complex than just, hot air rising in a room.
Okay.
Convection, at its most basic thermodynamic level, is the sudden, intense lifting of massive amounts of air and water. Let's break down the actual physics of it.
Yeah, let's do it.
So the sun heats the surface of the Earth. The air right above the ground gets hot. And because hot air is less dense than cold air, it becomes buoyant. It wants to rise, kind of like a hot air balloon.
Right, makes sense.
Now, if that air is holding a lot of evaporated water, so humidity, it carries all that invisible water vapor up with it as it rises.
Right, and as you go higher up in the atmosphere, it gets colder.
Exactly. And this is where the engine really ignites. As that warm, moist air rises up into the colder upper atmosphere, the atmospheric pressure drops, the air expands, and it cools down.
Okay, following so far.
And when it cools, that invisible water vapor can no longer stay a gas. It condenses back into liquid water droplets, and this is actually what forms cloud.
Right, okay.
But, and this is the absolute crucial piece of the puzzle here, when water changes state from a gas back into a liquid, it releases something called latent heat.
Wait, latent heat, what is that? Like heat that was somehow trapped inside the water?
Yes, exactly. Think about boiling a pot of water on your stove.
Okay.
You have to pump a lot of energy, the heat from your burner, into the liquid water to physically force it to turn into a gas, into steam.
Right.
That energy doesn't just disappear. It is physically stored in the vapor itself. So later on, when that vapor rises high into the sky and condenses back into a liquid droplet, it has to release all that stored energy back into the surrounding air.
Oh, wow. Wait, so the actual act of condensation heats up the air around it?
Precisely. And what happens when air gets heated?
It gets more buoyant, it rises.
Okay. It becomes even more buoyant. It rises even faster. So the very act of the cloud forming releases heat, which acts like an afterburner on a jet engine, causing the air to violently accelerate upward.
That is wild.
And then it pulls even more moist air up from the bottom to replace it, which then condenses, releasing more heat, causing more acceleration. It is essentially a runaway thermodynamic train.
That makes so much sense when you explain it like that. So convective mass flux is basically measuring that runaway train.
Yes, exactly. Convective mass flux is the measurement of that sheer volume of mass. We're talking billions of pounds of air and liquid water moving upward through a specific area over a specific amount of time.
Wow.
It is the raw vertical horsepower of the storm.
Okay, I want to try an analogy here just to see if I'm tracking this correctly.
Go for it.
Think of a thunderstorm like an elevator in a massive, towering skyscraper. Most of the time, our current weather technology is basically just standing down in the ground floor lobby. Like we have our rain gauges and our ground radar, and we can basically only see when the elevator doors open and the rain just spills out into the lobby.
Right, that's exactly how we do it now.
Or we have these traditional weather satellites that act almost like a helicopter hovering over the roof of the skyscraper.
Yes.
They look down and take pictures of the top of the elevator shaft. You know, the sprawling, flat anvil clouds at the very top of the storm. But we don't know what's happening in the middle.
Exactly. It's a huge gap.
So INCUS is designed to somehow look directly through the concrete walls of the building, straight into the dark elevator shaft to see exactly how fast that elevator car full of water is rocketing upward.
That is a brilliant way to visualize it. I really like that.
Oh, good.
Because we have been staring at the lobby and the roof for decades, making educated guesses about the middle part. But the action, the thermodynamic engine that actually dictates how violent that storm will be when it finally hits your neighborhood, that is happening entirely inside the shaft.
Right.
The speed of that elevator and the sheer mass of water it's carrying, that convective mass flux we just talked about, is the absolute key to unlocking the causality of these storms.
But So how does knowing the speed of the elevator actually change our understanding of the danger?
Well, because the vertical velocity dictates the severity of the fallout.
Okay.
If the elevator is moving slowly, say 10 or 15 miles per hour straight up, you might get a standard kind of dreary afternoon shower. The water goes up, it condenses, and it falls back down gently.
Right, just regular rain.
But if that elevator is rocketing upward at incredible speeds, and I mean sometimes exceeding 100 miles per hour straight up, it pulls millions of gallons of water and immense energy deep into the freezing upper atmosphere.
100 miles an hour straight up. That's insane.
It is violently fast. And that violent updraft actually suspends the water droplets high up in the freezing air, allowing them to accumulate layers and layers of ice, which is exactly how you get massive destructive hail.
Oh, so the hail is literally just trapped in the elevator getting colder and colder.
Precisely. And that explosive upward force is what stretches the atmosphere and creates the wind shear that spawns tornadoes. It creates torrential downpours and lethal microbursts.
So if we can actually measure the speed and the mass inside that elevator shaft, we get a completely different, highly accurate understanding of what the storm is actually capable of doing.
Exactly. But it's not just the movement itself. INCUS isn't just a speedometer for clouds, you know.
Right.
It is designed to correlate that vertical motion with a massive suite of other environmental factors. While it's measuring the updraft, the mission is simultaneously tracking the surrounding air temperature, the relative humidity, the atmospheric pressure, the wind speed, and the wind direction at all these different altitudes.
But why does it need all that extra data? I mean, if the goal is to measure the updraft, isn't just knowing the speed and the mass of the water enough to tell us if a storm is dangerous?
Well, knowing the speed of the elevator tells you what is happening right now. But knowing the condition of the cables, the voltage of the power supply, and the friction in the shaft tells you why it's moving that fast, and more importantly, what it's going to do next.
Ah, okay. The context.
Exactly. Let's look at wind shear, for example. Wind shear is the change in wind speed and direction at different altitudes.
Right, like the wind blowing east down at the surface, but blowing north up at 30,000 feet.
Exactly. If you have a powerful vertical updraft, but you have extreme wind shear ripping across the top of it, that shear might physically chop the top off the updraft, kind of choking the storm and killing it, before it ever becomes severe.
Oh, wow. I didn't think about that.
Right. Or, under slightly different thermodynamic conditions, that exact same wind shear might start twisting the updraft, turning that vertical column of air into a rotating mesocyclone.
And a mesocyclone is?
It's the parent engine of a supercell thunderstorm and eventually a tornado.
Oh, got it.
So by understanding how the humidity and temperature are fueling the lift and how the atmospheric winds are interacting with that vertical column, we move from just observing a storm to actually understanding the exact mechanical levers controlling it.
That feels like a monumental leap forward, honestly. Like we are going from just watching a storm happen on a screen to fundamentally understanding the exact physics that make it happen in real time.
It completely shifts the entire paradigm of global storm forecasting.
How so?
Well, right now, so much of our severe weather tracking is heavily reactive. A green blob appears on a radar screen. Over the next hour, it turns yellow, then dark red. An algorithm or a highly trained meteorologist interprets that color change, looks at the historical data, and issues a flash flood warning for your county.
But at that point, the storm is already dumping rain.
Right.
You're reacting to something that is already mature.
Exactly. We are reacting to the exhaust. But with the data INCUS will provide, meteorologists will actually be able to map the raw, underlying mechanics of storm formation before the heavy rain even starts falling.
Wow.
We are moving toward predictive models that are based on the fundamental physics of the updraft itself.
So instead of a weather anchor saying, hey, there's a really bad storm currently over the next town, it's headed your way, the models could theoretically say, hey, the thermodynamic conditions and the vertical mass flux of this cloud are aligning right now to create a severe destructive storm that will drop exactly 3 inches of rain on your neighborhood in exactly 34 minutes.
Precisely. We move from probabilities to mechanics, and the implications for that across human society are just staggering.
I can imagine.
Think about the decision makers who run our actual infrastructure. If you manage a massive hydroelectric dam or a reservoir system for a major city, you don't just need to know that it's going to rain today. You need to know exactly how millions of gallons of water are going to be dumped into your specific watershed and how fast.
Right, because if you guess wrong, the dam overflows and causes a flood, or you release way too much water too early and risk a drought later in the year.
Exactly. The stakes are huge. With predictive vertical modeling, you can proactively manage freshwater supplies with incredible precision. You can mitigate billions of dollars in property damage. You can coordinate emergency responses, evacuate specific floodplains, and even route air traffic with a lead time and an accuracy that is just currently impossible.
Okay, conceptually, I am completely sold. The value of measuring this vertical elevator is undeniable.
Good.
But as we get into the actual how, I start running into major logical roadblocks.
Okay, lay them on me.
Because measuring something that is moving that violently, spanning miles of atmosphere, and constantly changing second by second, that poses a massive logistical problem.
It does.
Like if you take a single static photograph of an explosion, you don't really understand the physics of it. To measure a vertical engine that is constantly accelerating and collapsing, a single snapshot isn't enough. You have to watch it evolve over time.
That's entirely correct.
Which leads us to the actual physical orbital design of the INCUS mission itself. And this is where my mind really starts to bend.
The orbital mechanics required to pull this off are truly something to behold. It is an absolute masterpiece of precision engineering.
So INCUS is not just one big satellite, which is what we usually expect from NASA, right?
Right.
It is a synchronized fleet. Specifically, it uses 3 small satellites flying in this incredibly tight, coordinated formation in low Earth orbit.
Yes, 3 of them.
And the spacing between these 3 satellites is what I just do not understand. The first and second satellites are separated by exactly 30 seconds of flight time.
Correct.
And then the second and third satellites are separated by 90 seconds.
Making a total continuous viewing window of exactly 120 seconds. 2 minutes.
Okay, I have to push back here.
Yeah.
Because the math and the logic feel super contradictory. First, why use 3 small satellites instead of just building one massive, super powerful flagship observatory? I mean, NASA's famous for these giant, school bus-sized, multi-billion-dollar satellites with massive power grids. Why chop the mission up into 3 tiny pieces?
That's a very valid question.
And more importantly, if you are doing that, why this incredibly specific, completely asymmetrical timing? 30 seconds and then a 90-second gap. That seems so strangely specific.
It is very specific, yes.
And beyond that, these satellites are orbiting at, what, 17,000 miles per hour?
Roughly 17,500 miles per hour, yes.
Right, and a thunderstorm has winds of maybe 50 to 100 miles per hour. So in the 120 seconds between the first satellite and the third satellite passing over, the storm has physically moved miles away from its original location, and the Earth itself is rotating underneath them. How are they even looking at the same thing?
Okay, these are excellent questions, and they honestly hit at the very heart of why this mission took so much engineering to design. Let's tackle the why 3 instead of 1 first. Okay, as you pointed out, a thunderstorm is a violently dynamic, constantly evolving system.
Yeah.
If you have a single massive flagship satellite orbiting the Earth at 17,500 miles per hour, it passes over a storm in a fraction of an instant.
Right, it's flying by super fast.
It can take one incredibly detailed, very high-resolution snapshot, but tropical convective storms evolve in a matter of seconds.
Right, the updraft can suddenly surge or just collapse completely.
Exactly. In the time it takes you to walk to your kitchen and pour a cup of coffee, an updraft can explode in intensity from a gentle lift to a severe destructive force. So a single snapshot from a massive satellite gives you the state of the storm at time 0, but it gives you no rate of change, it gives you no acceleration. You don't know if the storm is growing, dying, or just holding steady.
It's literally just a single frame of a movie. You can't tell the plot.
Precisely. To really understand a dynamic system, you need multiple cameras passing by sequentially. You need an orbital stop-motion animation. And that dictates the need for a fleet, and it specifically dictates that asymmetrical timing.
So the 120 seconds is on purpose.
Yes. The 120-second total window is the precise thermodynamic Goldilocks zone for witnessing a convective updraft evolve.
Let me try a different analogy for this timing, because the 30 and 90-second gaps so specific.
Go ahead.
Think about automotive engineers trying to analyze a high-speed car crash.
Okay, interesting.
If they just have 2 pictures, like a picture of the pristine car before the crash and then a picture of the mangled wreck 10 minutes later, they have absolutely no idea about the physics of the impact.
Right, they just see the before and after.
Exactly. To understand the safety systems, they need high-speed frames at incredibly specific intervals right when the crash happens.
That is a highly accurate comparison.
Okay, so the first satellite is like the camera capturing the baseline. It takes a reading of the storm at time 0, right before the crash.
Yes. It maps the vertical precipitation profile and the environmental state right as the sequence begins.
Then, exactly 30 seconds later, the second satellite flies over. And the reason it's 30 seconds is because in a car crash, you need a photo roughly 1 second after impact to see the crumple zone fail. Because the initial explosive transfer of energy happens basically instantly.
Yeah.
Is that what happens in a storm? Does it explode instantly?
That is exactly the physics at play here. Remember that latent heat we talked about earlier?
Oh, right. The boiling water analogy.
Yes. When that water vapor condenses and releases heat, the resulting acceleration of the updraft isn't some slow and steady buildup. It is an explosive, exponential surge.
Wow, okay.
That initial violent vertical velocity happens incredibly fast. So that specific 30-second window between the first and second satellite is designed to capture the immediate, rapid changes in the vertical speed of the air and water. It tells us the raw acceleration of the elevator right as the engine redlines.
So satellite 1 gives us the starting speed. Satellite 2, 30 seconds later, gives us the massive acceleration. It shows us the crumple zone failing in real time.
Yes. And then the third satellite arrives 90 seconds after the second one, which makes it 2 full minutes after the first satellite.
Okay.
This captures the longer-term evolution of the updraft. Has that violent 30-second surge sustained itself? Has the updraft collapsed under the sheer weight of the millions of gallons of water it just lifted? Or is that rising air now hitting the top of the troposphere and spreading out horizontally to form that massive anvil cloud?
So the 90-second gap is like looking at the car crash 10 seconds later to see where the debris actually landed.
Exactly. It is a perfectly choreographed sequence designed specifically around the physical timeline of atmospheric thermodynamics. You get the baseline state, the immediate explosive acceleration, and the sustained evolution and fallout, all mapped perfectly in a 120-second stop-motion orbital dance.
That is amazing. But what about the movement? You have 3 satellites screaming across the sky at 17,000 miles per hour and a storm moving across the ground. How do they physically look at the exact same spot 120 seconds later?
It comes down to the alignment of the orbital plane and the footprint of the radar beam itself.
Okay, how so?
Well, the 3 satellites are flying in the exact same orbital track in what we call a string of pearls formation, one right behind the other. And the radar beam they project down to the Earth isn't like a tiny laser pointer, it's a much wider footprint.
Ah, I see.
So while the Earth does rotate slightly and the storm does move a fraction of a mile during those 120 seconds, the swath of the radar beam is wide enough that the entire core of the updraft remains within the field of view for all 3 passes.
Okay, that makes a lot more sense.
Right, and then complex algorithms on the ground align the 3 images perfectly based on the GPS coordinates, creating a totally seamless time-lapse.
That is unbelievable. But to pull off a 120-second high-speed vertical stop-motion animation from the literal vacuum of space, these satellites need some highly specialized eyes.
They absolutely do.
You can't just slap a commercial digital camera onto a metal box and shoot it into orbit to look inside a cloud. Which brings us to the actual anatomy of these small sats.
Right.
And looking at how they are built, the hardware packed into these things is an absolute masterclass in miniaturization and, well, collaboration.
The sheer number of moving parts, both physically on the spacecraft and organizationally across the entire country, is staggering.
Right, because this isn't just one lab building everything in a basement somewhere. We have NASA's Jet Propulsion Laboratory, JPL, out in Southern California, who built the actual spaceborne radar.
Yes, the masters of radar.
We have a commercial company called Tendig, based in Louisville, Colorado, who built these deployable mesh radar reflectors. Then we have the middle satellite, which uniquely carries a microwave radiometer, also built by JPL. And all of this delicate, world-class instrumentation is packed into the actual spacecraft buses, the metal bodies of the satellites, which were built by Blue Canyon Technologies in Lafayette, Colorado.
The integration of all these disparate components into a unified, functioning fleet is an engineering marvel. I mean, it requires tolerances measured in fractions of a millimeter.
Let's focus on those tolerances, because the phrase deployable mesh radar reflector sounds completely wild to me.
It's an incredible piece of tech.
I look at that and I liken it to a high-tech pop-up tent. Because usually when we think of radar, especially deep space or high-powered weather radar, we think of massive, rigid, solid metal bowls.
Yeah, the giant dishes.
Right. Think of a satellite dish on the roof of a building but the size of a house. But these are small sats. They are roughly the size of a mini fridge. How do you physically cram world-class observatory-level radar equipment into a box that small?
The simple answer is you have to fold it up. And that is where the absolute genius of the deployable mesh comes in.
Okay, fold it up. How?
When you launch a rocket, the most expensive and limited resource you have is the volume inside the payload fairing, the nose cone of the rocket.
Right, there's barely any room.
Exactly. You cannot launch a massive, rigid metal radar dish on a small, cost-effective rocket. It simply won't fit. So the engineers at Tendeg designed these reflectors to be stowed incredibly tightly against the side of the spacecraft bus during the violent ride to space.
Okay, so it's packed down completely flat.
Yes. And once the satellites reach low Earth orbit and they detach from the launch vehicle, the mechanisms trigger and these reflectors deploy. They mechanically unfold, springing outward to form a highly tensioned parabolic dish.
Literally like popping open an umbrella when you step out into the rain.
Exactly like an umbrella. But here is the critical difference. This umbrella has to hold a perfect parabolic shape to fractions of a millimeter, while operating in the freezing cold and boiling heat of the vacuum of space, all while bouncing highly calibrated radar pulses deep into the Earth's atmosphere.
Sounds impossible.
It's not easy. The mesh itself is a specialized material, often a gold-plated molybdenum wire, and it's woven so tightly that the radar waves actually treat it as a solid surface.
Wait, how does that work? If it's a mesh, doesn't it have holes in it?
It does.
Why wouldn't the radar energy just pass right through the holes in the mesh? Like a sieve?
It comes down to the physics of electromagnetic wavelengths. The radar waves being emitted by the JPL instrument have a specific physical length.
Okay.
As long as the holes in the mesh are significantly smaller than a fraction of that specific radar wavelength, the wave physically cannot pass through the gap. The wave interacts with the mesh as if it were a perfectly smooth, solid sheet of metal.
Oh, that's brilliant. So it's a solid mirror to the radar, but it's light and flexible enough to fold up into a tiny box for launch.
Precisely. And this miniaturization and folding technology is exactly what makes coordinated multi-satellite missions financially and physically possible today.
Right, because otherwise it would be way too big.
Exactly. If you had to use traditional rigid metal dishes, you would need 3 massive rockets to launch them, and the cost would be absolutely astronomical. The deployable mesh democratizes the science.
But there is a massive quirk in this hardware lineup that we need to unpack. The 3 satellites in this orbital ballet aren't identical twins. Or, I guess, triplets.
No, they're not.
The first satellite and the third satellite are relatively similar. They both have the radar. But that middle satellite, the one that arrives at the critical 30-second mark to measure the explosive acceleration, is completely different.
Yes, it is.
It carries the radar, sure, but it also carries a microwave radiometer. Why does only the middle satellite have this, and what does a radiometer actually do?
To understand the radiometer, we have to look at the fundamental difference between active and passive instruments.
Yeah.
The spaceborne radars built by JPL are active instruments. They are actively shooting pulses of electromagnetic energy down into the storm, and then they wait to measure how much of that energy bounces back off the physical water droplets and ice crystals inside the updraft.
So the radar is taking a literal vertical X-ray of the elevator shaft. It's pinging the physical mass.
Yes. It gives you the high-resolution vertical precipitation profile. It shows you exactly where the dense water and ice are located, but an X-ray only shows you the bones of a system.
Right.
It doesn't show you the tissue, the blood flow, or the temperature of the room the patient is standing in, and that is exactly where the microwave radiometer comes in. A radiometer is a passive instrument. It doesn't send out pulses of energy. It simply opens its eyes and listens.
What is it listening for? Microwaves.
Yes. Specifically, it is measuring the natural microwave radiation being emitted by the Earth's atmosphere itself.
Wait, the atmosphere emits microwave radiation, like a kitchen appliance.
Yes, but on a much, much fainter scale. It comes down to Planck's law and blackbody radiation. Every object in the universe above absolute zero emits electromagnetic radiation based on its temperature.
Okay, I think I remember that from high school physics.
Right. And in the Earth's atmosphere, molecules of water vapor are constantly vibrating and rotating. As they vibrate, they emit incredibly faint signals in the microwave spectrum. The microwave radiometer on the middle satellite is tuned to the exact frequencies of those specific water vapor emissions.
So it can essentially see invisible humidity.
Exactly. By listening to these faint microwave whispers, the radiometer can measure the total amount of invisible water vapor in the entire atmospheric column. It can measure the liquid water content of the surrounding clouds and the environmental temperature profile.
Wow.
The radiometer provides the wide-angle atmospheric soup that the storm is swimming in.
Oh, I see. So the radar gives you the sharp vertical spike of the updraft itself, the bones. But the radiometer gives you the humidity and the temperature surrounding that updraft, the fuel that is actually feeding the engine.
Precisely. It acts as the thermodynamic anchor for the entire measurement. And you place it on the middle satellite because that gives you the perfect midpoint spatial context for the entire 120-second evolution.
That makes total sense.
Right. While the first and third satellites are getting the bookends of the vertical motion, the middle satellite is simultaneously capturing the explosive vertical acceleration and taking a massive wide-angle snapshot of the environmental fuel feeding the whole process.
The level of mechanical and orbital coordination here is just unbelievable. I mean, you have this intricately folded hardware packed with active X-ray vision radars and passive listening radiometers built by different academic and commercial teams across the country, all designed to fly in a perfect 120-second stop-motion dance.
It's a symphony, really.
But as anyone who has ever built a computer or renovated a house knows, building the individual hardware components is only half the battle. Ensuring that these delicate, high-tech pop-up tents actually survive being strapped to a controlled explosion and hurled into a deadly vacuum, that is the next massive hurdle.
Oh, the environment these machines must survive before they ever take their first measurement is remarkably unforgiving. The testing phase is often where missions literally live or die.
And the logistics of this pre-launch phase sound like an absolute nightmare. It is basically a high-stakes, highly fragile, multi-state road trip.
It really is.
In late 2025 and early 2026, all these components started shipping around the country. The radars left SoCal, went to Blue Canyon in Colorado for integration into the spacecraft buses. Then the first two assembled observatories successfully underwent their vibration and thermal vacuum testing. Then they were packed up in clean rooms and shipped back across Colorado to Tendig for test deployments of the delicate mesh reflectors. Then they were shipped back again to Blue Canyon for even more system testing. The third satellite doesn't even finish this gauntlet until September, and eventually they all have to be safely transported to NASA's Wallops Flight Facility in Virginia for the actual 2027 launch.
It is a relentless, exhausting logistical gauntlet. Every single time you move a spacecraft, you introduce the risk of contamination or physical damage, but the extreme testing at each of these facilities is absolutely, non-negotiably necessary.
I really want to talk about that testing gauntlet because the terms vibration testing and thermal vacuum testing are thrown around a lot. I know what a vibration is and I know what a vacuum is, but what does this actually look like in a laboratory for a multi-million-dollar satellite? Let's start with the vibration.
Launching a rocket into orbit is not a smooth elevator ride. It is incredibly violent. When you sit a payload on top of a rocket, you are placing it above hundreds of thousands of pounds of highly explosive liquid fuel.
Right, it's basically a bomb.
Essentially, yes. When those engines ignite, they don't just push the rocket up. They create an acoustic shock wave of sound and physical force that bounces off the launch pits and rips right back up through the body of the rocket.
Ouch.
The G-forces, the physical shaking, and the acoustic resonance inside the enclosed payload fairing are deafening and brutal. It is enough physical energy to vibrate delicate electronics into literal dust if they aren't engineered correctly.
So to test it, do they basically put the satellite on a giant subwoofer and just turn the bass all the way up?
That's essentially what an acoustic chamber is, yes. Through a massive mechanical shaker table.
Oh.
This table is programmed to simulate the exact physical frequency and amplitude profile of the specific rocket engine they will be launching on. They violently shake the spacecraft on all three axes, the X, Y, and Z axis.
And what happens if it fails? I mean, what is the weakest link here?
The weakest link is almost always the deployable mechanisms. Think back to that mesh radar reflector. It is folded up with springs, hinges, and tension cables.
Right.
During that vibration test, every single screw, every solder joint on the motherboard, and every folded hinge of that umbrella has to hold together perfectly. If the acoustic resonance hits the exact natural frequency of a single locking pin, and that pin rattles loose during launch, the reflector will not deploy when it reaches orbit.
Yeah, man.
It will stay jammed against the side of the bus, and a third of your entire mission is basically dead on arrival.
That is terrifying. You spend years designing this delicate instrument, and then you just physically shake the life out of it for hours to make sure it doesn't break. And if it survives that, it moves on to the thermal vacuum testing.
Yes, colloquially known in aerospace as the shake and bake.
Shake and bake. Nice.
Once it survives the physical violence of the launch simulation, it has to prove it can survive the environment of space. So they put the entire satellite into a massive steel thermal vacuum chamber. They seal the massive door, and powerful pumps suck all the atmospheric air out, dropping the pressure to simulate the hard vacuum of low Earth orbit.
And then what? Did they just blast it with heat lamps?
Yes, but the massive swings in temperature are what actually make it lethal. Low Earth orbit is an environment of intense, rapid extremes. Because there is no atmosphere to insulate the spacecraft or conduct heat away from it, the temperature is dictated entirely by direct radiation from the sun.
Okay.
When the satellite is on the day side of the Earth in direct, unfiltered sunlight, the temperatures on the hull can skyrocket to hundreds of degrees Fahrenheit above zero.
The metal is literally baking.
Exactly. But then, as the satellite travels at 17,000 miles per hour, it passes behind the Earth into its shadow, the night side.
And it gets cold.
Very cold. Without the sun, the temperature instantly plunges into the darkness of space, dropping to hundreds of degrees below zero.
And it does that orbit, what, every 90 minutes?
Roughly every 90 minutes. Imagine taking a piece of delicate electronics out of a roaring oven and immediately dropping it into liquid nitrogen over and over 15 times a day.
That would destroy my phone instantly.
The physics of thermal expansion become your absolute worst enemy. Materials expand when they get hot and shrink when they get cold. If the metal frame of mesh reflector expands at a slightly different rate than the mesh wire itself, the tension breaks.
Oh, right.
The parabolic shape warps, the radar beam loses focus, and your data is completely useless. Furthermore, electronics generate their own heat. Without air to carry that heat away via convection, the internal computers can literally cook themselves from the inside in the vacuum if the thermal radiators aren't perfectly designed.
It's just a punishing, rigorous environment. They have to absolutely guarantee that this intricate 120-second orbital dance will work flawlessly, because once it's up there, no human hands can ever reach it to tighten a screw or fix a jammed hinge.
That's exactly right. The testing phase is the only insurance policy you have.
As we talk through the sheer complexity of this, the JPL radars, the Blue Canyon buses, the Tendig reflectors, the Wallops launch facility, it really highlights how many different names, companies, and disciplines are involved in this one single project.
It's a huge ecosystem.
Right. It's not just a bunch of guys in white lab coats in a single NASA basement anymore. And this leads directly into something that I think is fundamentally changing the entire way we explore our own planet.
The organizational structure and the philosophy of this mission are just as innovative and, frankly, just as important as the hardware itself.
Right. So the NSEUS mission is led by a principal investigator, Sue Vanden Heuvel, out of Colorado State University in Fort Collins.
Yes, she's brilliant.
It is part of NASA's broader Earth System Observatory program. But specifically, it belongs to an architecture called Falcon. That is an acronym that stands for Fleet for the Atmosphere, linking commercial observations with NASA.
Yes, Falcon.
So what does that actually mean in practice? What does it mean to be actively linking commercial observations with NASA in this specific way, and why is that a big deal?
This touches on one of the most critical evolutions in the history of space exploration and Earth science. Historically, if you look back at the grand era of Earth observation satellites, the 80s, the 90s, the early 2000s, the paradigm was almost entirely monolithic.
What do you mean by monolithic?
I mean, massive, singular, and highly centralized. NASA would identify a broad scientific need. A single NASA center would spend years designing the instruments. Then, a massive, traditional aerospace prime contractor would be hired to build an enormous, multi-ton spacecraft bus just to house it.
Right.
It would take 15 to 20 years of development, cost billions of dollars, and launch as a singular flagship mission.
Like the Landsat satellites or those massive weather observatories?
Exactly. And to be clear, those are incredible machines that have provided invaluable data. But the monolithic paradigm has massive, massive drawbacks. It is agonizingly slow to develop, it is unspeakably expensive, and most importantly, it creates a terrifying single point of failure.
Oh, because if it breaks,
If that one rocket explodes on the launch pad, or if one critical instrument fails to deploy in orbit, 2 decades of science and billions of dollars evaporate instantly. The entire field of study stalls out for another 20 years while they try to scrape together the budget to build a replacement.
That is a terrifying way to do science, putting all your eggs in $1 billion basket.
Precisely. The shift we are seeing now, which is perfectly embodied by the Falcon architecture, is the shift toward the fleet mentality. It's about agility, modularity, scalability, and interconnectedness.
Okay, I like those buzzwords.
By intentionally linking academic institutions like Colorado State University, commercial space partners like Tendig and Blue Canyon Technologies, and traditional government centers like JPL, the science becomes vastly more nimble and resilient.
So instead of NASA having to invent the entire spacecraft bus from scratch and design every single thruster and solar panel, they can just go to the commercial sector.
Exactly.
They can go to a company like Blue Canyon who says, hey, we already mass-produce these highly reliable, standardized, small satellite buses. Just bolt your GPL radar onto the top of it.
That is exactly the model. The commercial space sector over the last decade has driven the cost of access to space and the cost of standardized satellite components down to a tiny fraction of what they used to be.
Which is awesome.
It is. NASA can leverage that relentless commercial speed and manufacturing efficiency while still providing the world-class, bespoke scientific instruments that only a place like JPL has the expertise to build. And crucially, the principal investigator at the university gets to focus almost entirely on the science, the data, and the meteorology, rather than spending their entire career managing a monolithic, decade-long engineering program.
It's almost like building an observatory with commercial Legos, but on a massive governmental and academic scale.
And the word fleet in Falcon is the most crucial part. INCUS is one specific mission looking at updrafts, but it is part of a much larger overlapping network of atmosphere-observing satellites.
Right, there are others.
By utilizing cheap commercial smallsats, NASA can launch dozens of smaller targeted missions. They combine data from different hardware contributions across this entire fleet. If one satellite in the fleet fails, you lose a tiny fraction of your data, not the entire mission.
You don't lose the whole science program.
Exactly. You start to build a continuous, real-time, highly resilient, three-dimensional model of the Earth's atmosphere, fed by a swarm of sensors, rather than relying on one giant satellite that only passes over your city every few days.
And bringing this all back to you, the listener, sitting in your car or walking your dog right now, this interconnected fleet mentality is exactly what is going to power the future of your daily life.
Absolutely.
This agility, this constant overlapping stream of data from commercial and NASA sensors, is what will eventually drive the weather alerts right on your phone. It is the fundamental difference between getting a broad, vague warning that your general county might experience heavy rain sometime tonight versus an urgent, incredibly precise alert that a specific, catastrophic flash flood is going to hit your exact neighborhood in 22 minutes.
It's the democratization of data. The transition from massive monolithic science to this agile, interconnected fleet is what takes these complex atmospheric discoveries out of the esoteric academic journals and puts them directly into the hands of emergency managers, city planners, and the public.
It's what helps your local government know exactly when to open the spillways on the reservoir, saving millions in infrastructure damage and preserving the drinking water you rely on for the rest of the year. So to pull all of these complex threads together, we are looking at a very near future where we are launching a synchronized, high-speed orbital ballet of small satellites. We are using commercially supported deployable pop-up space radars to take a perfectly timed 120-second stop-motion X-ray of the violent vertical engines that drive our global weather. We are finally peering inside the invisible elevator shaft of the tropical convective storms that simultaneously give us life and threaten our cities.
It is a monumental, hard-fought leap forward in our understanding of the planet's thermodynamic engine. But if we project this capability forward, if we follow the logic of the science to its ultimate conclusion, it actually leaves us with a truly profound and maybe even slightly unsettling thought to consider.
Oh, wow. Okay, what's that?
Well, if the INCUS mission and the massive, broader Falcon fleet that follows it eventually allow us to perfectly map the exact seconds the storm decides to become destructive.
Right, if we know exactly what it's doing.
Exactly. If we truly understand the thermodynamic levers, the precise convective mass flux, the humidity and the wind shear that tips a storm from a gentle rainmaker into a catastrophic, lethal event, How long until humanity moves from simply forecasting severe weather to actively trying to intervene in its development?
Oh, wow. I didn't even think of that.
If you know the precise moment, the exact minute and location where that updraft engine is redlining and accelerating toward a tornado or a massive hail event, do you just watch it happen and send out a siren warning? Or, as the technology catches up to the predictive models, do you eventually try to physically throw a wrench into the elevator shaft?
Like, actually stop it.
Do you seed the cloud, alter the temperature, or somehow disrupt the shear before it kills people?
Weather modification based on perfect real-time predictive mechanics. That is a massive, incredibly heavy thought to leave off on. Well, as we all keep watching the lobby doors open and the rain fall down, at least now we know there's a synchronized fleet of satellites getting ready to look inside the concrete walls of the skyscraper. Until next time, keep looking up.